Good morning and welcome back, students. So today we'll talk about another topic, and that is Fresnel Biprism. So in this course we are studying interference and diffraction, and we are in the interference by division of wavefronts. So this experimental setup, Fresnel Biprism, again advocate the interference by division of wavefront. So as the name suggests, it is a biprism, two prisms. Bi means two, so biprism. So in the construction of this biprism, there are two prisms, and these two biprisms are connected back to back, and this angle is 179 degree, and these two angles are 30 minutes each. So when you shine this biprism sharp edge using a source of monochromatic coherent light, so these rays will go like that, and somewhere here you have positioned the screen. This is screen, and when it is seen from the screen, it appears that the light is coming from S1 and S2, two distinct sources. So in this region on the screen you will get maximas and minimas. So again, this distance is, let us say, capital D. These two sources are at a distance S1 and S2 at small d, and we are using wavelength of light lambda. So as in the Young's double slit experiment, we have deduced the formula fringe width beta equal to lambda capital D upon small d. Likewise here we have the same formula, because now it becomes very similar geometry, and the mathematics of this will be this. So this beta is the fringe width, lambda is the wavelength of light, d is the distance between the source and the screen, and small d is the distance between the two distinct sources S1 and S2 made up of single source S. So the important thing here is the two sources are made up of the single source S, and the distance between the source and screen is like capital D. And to perform this experiment, what we require is the following. We should have a monochromatic source, as we have source S of wavelength lambda. The sources S1 and S2 are made up of the single source, monochromatic coherent source, and the thing which is important is the orientation of these, the alignment of these distance points. The source should shine this edge of the prism, sharp edge of the prism, and the alignment is very important. There are tangent screw attached to the biprism so that the sharp edge of the biprism is exposed using the source S. So these S1 and S2 are generated with the refraction effect, and these are two virtual sources. These are not actual sources, these are virtual sources made up of source S and S. The application of this biprism is in the measuring the wavelength of light. If I make it again, this is source S, this is biprism, this is very slant angle, and we are exposing it with the source S, and light will go like that. Screen S, and it appears from the screen that the light is coming from two sources S1 and S2. So we have the formula beta equal to lambda capital D upon small d. So in this formula, if we know wavelength of light, if we know the distance between the source and the screen, and the distance between the two distinct sources S1 and S2, we can simply calculate what is the fringe width. Or any other three things out of this four term formula, we can find the term which is left. So now let us talk about the measuring capital D. So capital D is very mathematical. You know that the point, this point somewhere here and somewhere here. This is the distance D, capital D. So it is sometimes also written as U A plus B. A is the distance between the source and the biprism. B is the distance between the biprism and the screen. Another thing is the measurement of small d, the distance between the two sources. So to measure this, what we'll do is, in this biprism, basically we have this geometry. Source S is signing these two source biprism, and S1 and S2 are the two distinct sources. So light is going like that. So to measure, so this is biprism, and somewhere here I am positioning the first convex lens, let us say L1, and this is the screen. So when I view these sources S1 and S2, this is, let us say, U, and this is, let us say, V. So on the screen, using a tangent screw attached, when I move this, I find the distance is, let us say, D1. So D1 by D equal to U upon V. D1 is the measured distance between the sources S1 and S2. So it is like this way, light is going in this way. So this is, let us say, D1. D1 is the measured distance, D is the actual distance, U upon V is the distance between the source to the convex lens and the distance between the image to the convex lens. Likewise, I'll put this lens at somewhere here. I will remove this and I'll apply this. So this is so chosen, this distance equal to V and this distance equal to U. The lens from this point is now positioned at that point. So when light will go, it will be like that. It will cross this point. So this lens is not here. So now this distance becomes D2. The distance between the 2 points S1 and S2 is D2. So we'll get formula D2 by D equal to, so see, now U and V are interchanged, so it will become V upon U. So when you multiply these two equations or the formulas, I can write D1 times D2 upon D square equal to 1. So D equal to square root of D1 into D2. So to measure small d, this is the procedure. You just multiply, you measure the D1 and D2, multiply them and take the square root. So now in this formula, beta equal lambda capital D upon small d. If we know the wavelength of light, and we have calculated capital D and small d, we can simply tell what is the fringe width. Otherwise, if we want to calculate lambda, we can write it beta small d upon capital D. If you know the fringe width, I told you it is the distance between the two sharp maximas or the minimas. So it is that. This is fringed with beta.